Okay, this is part 147. We're still on line 18A3Z section. And I've added some numbers and letters to confuse you all. No, seriously, I didn't try to, but I'm confused myself. But that's beside the point. So this one's going to be called line 18A, 3Z, 2A, and then 3A. Because obviously, if you see an A beside the number, that means there's going to be a B. Okay? So it means there's more than one video with this section. So, Sparticles. These are new. Brand spanking new. They just came out in February 2012 from what I can, unless I've missed something. Well, I found some data from 2012 that was just posted actually a week or so ago. So, Sparticles, dark matter, Squarks Gluinos SNeutrino SUSY, or SUSY, sorry. Atlas, ATLAS, those are names of particle colliders. LHC, that's the Large Hadron Collider. And then 5G Wow Seti, again, 5G stands for formula. There's a formula in here. Okay? Or something, sorry, UFO 5G means there's an actual formula. 5G means that there's components to the formula that can be used with the formula that I've come up with, okay? Here's the alien Wow Seti signal. And here's a pretty picture. Okay? So this is visualization of a recent collision captured by the Atlas detector. That's from the Atlas team. And I believe there was CERN, because the two names seem to come up together. And that's at www.phys.org.com. And actually, sorry, this one was posted March 7, 2011. Oh, I must have found another one. This is by Pete Wilson, Oxide blog, okay? Okay, so high energy physics experiment, search for Squarks, I don't know what it is. Squarks, how's that sound? And Gluinos, using final states with jets. Emitting transverse momentum with the Atlas detector and SQRTS equals 7 TeV proton-proton collisions. The Atlas collaboration. That's the name of the team, and they submitted this on February 25th, 2011. So it says a search for Squarks and Gluinos is in final states containing jets, missing transverse momentum, and no electrons or muons is presented. The data were recorded by the Atlas experiment and Squarks equals 7 TeV proton-proton collisions at the Large Hadron Collider. I said Hadron, didn't I? Sorry. Hadron Collider. No excess above the standard model background expectation was observed in 35 inverse picobarns of analyzed data. Gluino masses below 500 GeV are excluded at the 95% confidence level. In simplified models containing only S-quarks of the first two generations, a Gluino octet and a massless neutralino. Again, we're looking at some data that came up with the SETI signal, okay? The exclusion increases to 870 GeV for equal mass S-quarks and Gluinos. There's some more data for you to look at. So it's about the limits. Okay? That's the name of there. And I found a photo for you on someone else's blog. He's got it all. So this is in the Science Photo Library. I found it on a blog post. I was looking for an image just to see what it looks like. So this is a visualization of prime orbital quark gluon plasma. And it's from Archimed Science Photo Library. It says, caption is visualization of the early universe. This image depicts particles in the quark gluon soup, which existed less than 1/1,000,000th of a second after the Big Bang. Quarks are shown in red, green, and blue. Antiquarks are sigma, magneta, and yellow. Okay? Other colors are gluons. The gray particles are electrons and electroweak force bosons. Gluons are the carriers of the strong nuclear force, but at the high energy density of the universe at this time, a million billion degrees temperature, quarks would not have been confined by the force. As the universe continued to expand and the temperatures dropped, the quarks were able to combine with baryons such as protons and neutrons. This is from www.sciencephoto.com. Okay. So now I've got a PDF file for you to look at. We've got high energy physics, phenomenology, light S-neutrino dark matter at the LHC. It's from Genevieve Belanger, Sabine Kram, and Andre Lessa. And that was posted May 24th, 2011. And supersymmetric SUSY models with Dirac neutrino masses, a weak scaled trilinear A term that is not proportional to the small neutrino Yukawa, I guess that's another neutrino, couplings, can induce a sizable mixing between left and right-handed S-neutrinos. The lighter S-neutrino mass ion state can hence become the lightest SUSY particle, LSP, and a viable dark matter candidate. In particular, it can be an excellent candidate for light dark matter with mass below 10 GeV. Such a light mixture S-neutrino LSP has a dramatic effect on SUSY signatures at the LHC, as charginos decay dominantly into the light S-neutrino, plus a charged lepton, and neutralinos decay invisibly to a neutrino plus a S-neutrino. We perform a detailed study of the LHC potential to resolve the light S-neutrino dark matter scenario by means of 3 representative benchmark points with different Gluino and S-quark mass hierarchies. We study in particular the determination of the LSP S-neutrino mass from cascade decays involving charginos using the MT2 variable. Moreover, we address measurements of additional invisible Sparticles, in our case the lightest neutralino, and the question of discrimination against the MSSM. It was my first time hearing the word Sparticles. Never heard of it before until today. Okay, so there's more details about this journal. That's there. So February 21st, 2012, my thoughts. Quote, moreover, we address measurements of additional invisible Sparticles, in our case the lightest neutralino, and the question of discrimination against the MSSM. My thoughts continue. They have found a way to find invisible particles. They are called Sparticles. Then it says the lightest neutralino. Not sure what that means. I googled MSSM to find out what it stands for. The minimal supersymmetric standard model is the minimal extension to the standard model that realizes n equals 1 supersymmetry, although non-minimal extensions do exist. Supersymmetry pairs bosons with fermions. Therefore, every standard model particle has a partner that has yet to be discovered. Interesting that bosons and fermions have come up earlier in the data, all the way back to line 15. They were mentioned several times. If the superparticles are found, it is analogous to discovering antimatter. And depending on the details of what is found, it could provide evidence for grand unification. It might even in principle prove hints as to whether string theory describes nature. Now, you remember string theory also comes up with black holes and white holes, and it connects the two, and also wormholes. All that stuff is connected, so it's interesting that that came up too. And I found this lovely picture, and it says a CMS experiment at LHC CERN. It was recorded Tuesday, October 26, 2010. So this is a 3-jet candidate SUSY event. It's seen by the CMS detector, October 2010. Okay, and that's at www.3.imperial.ac.uk, high energy physics. February 21st, 2012, my thoughts. The word SUSY has come up several times. I'm going to take a look at it on Google. SUSY stands for supersymmetry. This is a keyword in the lines of Wow Seti data. This data is found in Go to the Light, to be numbered and filmed in future. Line 24 and an 18A3S4 and then 18A3Z3S3A. That's the line number. What is SUSY? What's it stand for? Supersymmetry is an extension to the standard model of particle physics that postulates the existence of additional massive weakly interacting particles. Supersymmetric particles are Sparticles. Dubbed the last space-time symmetry, every matter-particle fermion in the standard model gains a complementary force-carrying bosonic Sparticle, and every boson gains matter-like supersymmetric fermion. Some therefore see supersymmetry as a way of mathematically unifying matter and forces. Supersymmetry also helps to resolve some problems with the standard model. Sparticles also provide candidates for the elusive dark matter thought to make up some fifth of the known universe. And again, that's from the imperialac.uk website. Quote, in particle physics, supersymmetry, often abbreviated SUSY, is a symmetry that relates elementary particles of one spin to other particles that differ by half a unit of spin and are known as superpartners. In a theory, so here's a theory, with unbroken supersymmetry, for every type of boson there exists a corresponding type of fermion with the same mass in eternal quantum numbers and vice versa. So they're trying to prove this theory, and as far from what I've seen from the data, it still hasn't been proven yet. If it has, let me know and I'll look it up, okay, and I'll blog it for you, okay? There is no direct evidence for the existence of supersymmetry. I don't know how old this Wikipedia thing is. Things could have changed. I know there's some new stuff coming out in 2012 where they're saying they are starting to prove it, so bear with me. It is motivated by possible solutions to several theoretical problems, since the superpartners of the standard model particles have not been observed. Supersymmetry, if it exists, must be a broken symmetry, allowing the superparticles to be heavier than the corresponding standard model particles. So before they were trying to prove they had the same mass and the same internal quantum numbers, and now they're saying they might have different masses. The LHC has now extended this experimental limits and partially excluded these ranges with no sign of supersymmetry. So basically they removed some of the equations. Based on the data sample collected by the CMS detector at the LHC through the summer of 2011, MSSM S-quarks have been excluded up to the mass of 1.1 TeV, and gluinos have been excluded up to 500 GeV. MSSM predicts that the mass of the lightest Higgs boson should not be much lighter than the mass of the Z boson. And in the absence of fine-tuning, with the supersymmetry breaking scale on the order of 1 TeV should not exceed 130 GeV. Furthermore, for values of the MSSM parameter, it predicts Higgs mass below 114 GeV over most of the parameter space. This region of Higgs mass was excluded by LEP by 2000. So that's year 2000. It's 12 years later. So that explains it. This is 12 years old. Can somebody please update Wikipedia? Seriously, it needs updating. As of December 2011, oh, there we go. We got some updating, right? Preliminary results from the LHC point towards a possible Higgs with the mass around 125 GeV. So it took them 11 years to find that out? Wow. Okay. This is seen as somewhat problematic for the minimal supersymmetric model, as the value of 125 GeV is relatively large for the model and it considerably constrains the parameter space. Sorry, I had to read all that because we need to know what the measurements are for this Higgs mass and get an idea of what it needs to be at in order to get use this for the equations. Z boson did come up in line 18, and Higgs boson has come up before too. So I'm going to need to cross-reference those two and see what they come up with to see if we can put that into a new equation. I'm going to make a note here, Higgs, and I need Z boson. Okay, so I'll have to Google those two, or sorry, just to see what I can get. Okay. And let's see. There are two categories of identical particles: bosons, which can share quantum states, defined by a unique set of quantum numbers, and fermions, which are forbidden from sharing a quantum state. That's strange. They're trying to prove that they have the same quantum state, or internal. Okay, I don't understand this, because if you're saying that fermions are forbidden from sharing a quantum state, this property of fermions is known as the Pauli exclusion principle. That's interesting, because I remember seeing the Pauli exclusion principle, and I think there was a test result that questioned it, but I'm not sure what it was. I'm going to write that one down, just in case I can find it, okay? I probably didn't put it in with my data, so I might have to look for it on Google. Again, a lot of the stuff I don't pick up because I don't know what it is, and then it's like, oh, okay, I remember that. So this is on electron6.phys.utk.edu. Okay, that's their website there. And here's a fella here. He wrote LHC results, put supersymmetry theory on the spot. I pulled some of the stuff he talked about because he brought up some interesting points. So it's from Palab Ghosh, science correspondent, BBC News. And it's from the website www.bbc.co.uk. And he's got a pretty picture on his blog there. So supersymmetry predicts the existence of mysterious superparticles. I really liked what that said, because it gives you an idea of that there's some powerful particles out there that they still haven't figured out how they work. So this is a quote from Palab Ghosh. If supersymmetric particles exist, B mesons ought to decay far more often than if they do not exist. Okay? There also ought to be a greater difference in the way matter and antimatter versions of these particles decay. The results have been eagerly awaited following hints from earlier results, most notably from the Tevatron particle accelerator in the US, that the decay of B mesons was influenced by supersymmetric particles. And that's from his website, bbc.co.uk, and it's Science Environment 1468050. Okay, so he has a theory that they don't exist. So let's look and see. And I found this PDF file. High energy physics experiment. Supersymmetry searches at the compact muon solenoid CMS experiment 2011. Essay Koi CMS collaboration submitted February 5th, 2012. So it was only, so they did the testing in 2000 and they're just giving the results out now. So the discovery, inclusion of supersymmetric models for fundamental interactions of particles is one of the milestones targeted by the Large Hadron Collider, LHC, and in particular comprises of a large part of the physics program of the CMS experiment. Since the initial measurements using the 36 IPB of integrated luminosity delivered by the LHC in 2010, presently available results utilize about 1/5 of the data delivered in 2011. They've only gone through 1/5 of the data from the, okay, so they got a lot more data to go through yet. So we could be getting some more test results and probably in the next month or so. In the ballpark of 1 IFB, significantly extending the world limits placed on Gluino and S-quark production signals. An overview of these analyses is presented, highlighting 4 that have been newly made public as of the date of this conference. The evidence for supersymmetry, SUSY, is still elusive, and a discussion follows as to where current searches have not yet probed. So they're talking about it and trying to figure out how to prove it. Also pointing out where they might have difficulty ever probing without dedicated arguments. And it's presented at the 2011 Hadron Collider Physics Synopsium, Paris, France, in November 2011. So yeah, they've only got their data up to 2011. They've only done 1/5 of the data, and they're probably going to find some more. So February 21st, 2012, 10:42 p.m. Ouch. Sorry, my hand's getting sore from holding the camera. My thoughts, quotes of key phrases. Sorry. It's 1 o'clock. Oh, 1:41 a.m. Maybe that's why I can't talk straight. Okay, for every type of boson, there exists a corresponding type of fermion. Some mass and internal quantum number. No direct evidence for the existence of supersymmetry. As of December 2011, preliminary results from the LHC point towards a possible Higgs with the mass around 125 GeV. So they're saying from the results so far, they're saying there is a possibility. So, but this is seen as a somewhat problematic for the minimal supersymmetric model, as the value of 125 GeV is relatively large for the model, and it considerably constrains the parameter space. So I guess they're trying to get it smaller than that or something. I wish I knew what this meant. In this line of data, we learn the differences between bosons and fermion and how they relate to one another. The fact that they are still trying to prove the supersymmetric theories in 2012, I believe they are coming close to it. Many of them say they have to find a different equation in physics. That's the same thing I've been saying in all these videos. Look outside of the box. Don't rely on past physics formulas. They won't jive with recent technology. Most of these theories came out in the 17th century. Although most of them still hold to be true, many are being changed and questioned based on the data and results we are finding in the Wow Seti alien radio signal. What I'm basically talking about is the data coming up from your recent test results. They're questioning a lot of the physics formulas, and there's quite a few that are changing because of your test results. So again, it's a new era, it's a new age, and I believe you're going to come up with some new technology ideas in 2012. Some huge changes are going to take place. According to the Mayan calendar, that's what they're saying is going to happen. And so did Nostradamus as well. Could it be they are trying to tell you something? That there's more to learn here? You can develop the new formulas and equations. I've given you proof from the forums where scientific people chat about their theories and calculations. They should write up papers about these theories and calculations and have a website for collider facilities to take a look at. A huge compiled worldwide database with a set of keywords to bring up the search engine results. Then you take the different equations and pull out the ones that go with whatever particle you are testing. A combination of world knowledge will help you find the answers quickly instead of 5, 10, 20, 30 years' time. Finding the data about SUSY and Atlas, I've seen those names several times before, but didn't really pay attention what it was trying to tell me. I didn't take the time to research the keywords to find out it's based on 2012 results. I wish I had. I'm sure whatever is important will pop up in here sooner or later. We have up to 27 lines of math equations, and I'm still in line 18A section. There's 18B to Z data to be researched for yet, and so on. And that's just my tags. Okay? So we'll be going on to the next video here. And yeah, I did that picture there. Okay, and I'm down to my last bar here of power, so hopefully we'll make it.